Hi, in this video, I want to go over Venn diagrams and I want to start at the beginning. What does a Venn diagram represent? How can it be used to represent sentences in categorical logic? And how can Venn diagrams then be used to show that an argument in categorical logic, a simple two-premise argument, a syllogism, is valid or invalid? So again, let's start at the beginning. Imagine that this square here represents the universe, represents concept space, represents everything that exists. And at this point, there's no structure imposed at all on that concept space. It's just a chaotic, meaningless mess, void of ideas, objects, entities. There's no structure to it. So next, let's see what happens if we add some structure. Now imagine that to my universe, I have invented one single category. This category is now in my conceptual space for making sense of my universe. Presents the category. It represents a little. This circle represents some way of carving up my world, some way of categorizing the things in my world. So let's say that the way that I've categorized things in my universe is, let's use the category of dogs. In that case, this circle represents, again, the category of dogs. So when I see an object in my world, if it is a dog, it goes in this circle. If it's not a dog, it goes outside of this circle. So everything in the entire universe must go either in the circle or outside of the circle. It's either a dog or it's not a dog. So this circle can represent any category that I like for making sense of my world. Whatever category I'm representing with the circle, inside of the circle belongs every entity or object in the universe that is in the category, and outside of the circle is everything else. That's why this square here can represent the entire universe. I'm just dividing up the universe for purposes of my current project into dogs and non-dogs. All of the dogs I'm going to place inside of this circle. All of the non-dogs I'm going to place outside of the circle. So I just put a table, goes out here. I go out here. My phone goes out here. My house goes out here. Anything that's not a dog belongs outside of the circle. A cat goes out here. Anything that is a dog goes inside. Okay, so that's what the circles are in this system. The circles represent categories or classes of objects. So let's go to what if, oh, I didn't know it would keep my annotations on the next one. So erase all. What if I don't just want to divide my world up only into dogs? What if I have another category that I bring on board and I want to think about where everything now fits in my world of categories? So I still have my dogs category, but I also have another category that I want to be able to place objects in. My other category is, it can be anything. It can be anything that you like. I'll make one that will have, actually, I'll make one that I'll do the set of brown things for this blue circle. So I now have two categories. So now I have, instead of on the previous example, I had everything in the universe belonged either within the set of dogs or outside the set of dogs. Now I actually have 4 different locations an object I encounter might belong in my category space in my head. If it's brown, but it's not a dog, so my phone isn't brown. Let's think of a clod of dirt, a handful of soil is brown, but it's not a dog, so that belongs here. If it's brown and it's a dog, like a chocolate lab, like a dog named Bailey that I know, Bailey belongs here because she's both brown and a dog. If it's a dog, but it's not brown, if it's a golden lab, like a dog named, like a dog named Ronnie that I know, he's a dog, but he's not brown, so he belongs here. Now, if it's neither brown nor a dog, like my phone is currently lavender, so it's not brown. My phone is also not a dog, so it's not a dog. So it belongs out here. Many things belong somewhere out here in the space of things that are non-brown and non-dog. If it's brown, but it's not a dog, it belongs here. If it's a dog and it's brown, it belongs here in this overlap of the 2 circles. And if it's a dog and it's not brown, then it belongs over here. So each region of space represents a conceptual possibility, a possible intersection of categories that an object can fit into. Okay? And this is important because, first of all, there's a reason why when we're doing categorical logic, we tend to oversimplify things in this way, right? Because in reality, I have many more categories in my conceptual apparatus than just 2. But it would be a long project to try to spell them all out and place them all on the same diagram like this one. So we're breaking it down to the simplest possible parts so that then we can understand the logical relationships between categories at a most basic level. So let's move to that, thinking about logical relationships between categories. Some categories, like brown things and dogs, there aren't any logical truths I can assert between the relationships of brown things and dogs, other than, the fact that each one of these regions has at least one thing in it is an important thing that I could say. And so we'll get to looking at what that would mean for categorical logic, for sure. But one of the important tools of categorical logic is telling me something about concept space. So there are a few different types of things about concept space that categorical logic can tell us. So let's go over each of the 4 different types of claim and what it can tell us about concept space. So again, each of these circles represents a category or a class of objects. Let's say in the first case, to represent an A claim, let's say that our subject class is cats. So this blue circle represents the set of all cats. This green circle represents the set of all mammals, let's say. Okay, so again, everything in my universe goes somewhere on this concept map, right? If it's a cat but not a mammal, it goes here. If it's a cat and a mammal, it goes here. If it's a cat and if it's a mammal but not a cat, it goes here. And if it's neither cat nor mammal, it would go somewhere on the outside of these circles. What do you notice about this particular diagram? What do you notice about the things that I just said? We can imagine many non-mammal, non-cats. Again, my phone is neither mammal nor cat. That can go here. We can imagine many mammal, non-cats, like the dogs I mentioned on the previous example. Bailey's a dog. Bailey goes here. Also imagine many mammal cats, any cat you can imagine. So my cat's name is Lance, he goes here. But what about a non-mammal cat? Well, that doesn't make any sense. There's nothing in region 1 of space here. Why? Because all cats are mammals. So we have a special tool within categorical logic for representing a claim like this. It tells me that this region 1 of concept space on my diagram has got to be empty because all cats are mammals. This is true. What does it mean to say that's true? It means there's nothing in this region of space here. So the convention within the Venn diagram system within categorical logic is to shade this region because shading it tells me nothing can go there. Nothing can go here. I'll cover it up so that I know that nothing belongs there. No entities are non-mammal cats because of the fact that all cats are mammals. So this gets shaded. And that holds for any sentence of this form. Any sentence with the form all S are P means that there's nothing in the S but not P region, this region over here of space. So that's one type of categorical sentence. This has a name. Each categorical sentence type has a name. This one is called an A claim. A claim is universal because it makes a claim about all of something. It makes a universal claim about the set of all cats. And it's also affirmative. Because it's making a positive claim about a universal set of things. So an A claim is universal affirmative because of the fact that it says all, which is both, again, a universal thing that it applies to everything of something, and it's an affirmative claim saying everything of something is something. Okay, so that's the first type of categorical proposition, and that's how we represent it on the diagram, and that's why. Let's go to the next type. I'll erase this. Erase, erase, erase. Oops, I could keep that S there. Okay. Well, let's look at another possible categorical relationship. In this case, let's say that the blue circle represents reptiles. Reptiles as a category. So as a snake, any particular snake would be in here, right? Our green circle, let's just stick with dog. It's an easy example. So Bailey goes over here. And as always, based on how these circles represent the world, anything within the blue circle is a snake, or I mean, anything within the blue circle is a reptile. Anything within the green circle is a dog. So, I just realized, okay, there we go. Sorry about that video overlay going over the words. Hopefully you can see it now. So, if everything within the green circle is a dog and everything within the blue circle is a reptile, that means this crescent-shaped region of space represents all of the reptiles that are not dog. This middle lens-shaped region of space represents everything that's both reptile and dog. And this right-ermost crescent-shaped region of space represents everything that's a dog that's not a reptile. And again, the outside region represents anything that's neither reptile nor dog. Again, my phone is out here, Bailey's here, the snake is here. The center region of space, I said, represents the set of things that are both reptile and dog. What do we know about that region based on what we know about the category of reptile and the category of dog? Well, just as we knew previously, the region of cats that are not mammals was empty. Here, we know the region of things that are both reptiles and dogs is also empty. So to indicate when a region of space on our concept map, category concept map is empty, we can shade that region. How do we know this region is empty? And we know this region is empty because we know it is true that no reptiles are dogs. Because reptiles are a totally different category than dogs. There's no overlap between reptiles and dogs, just based on what we know about those concepts and how they're defined. So this middle region of space is shaded to indicate that nothing can go there. This type of claim is called an E-claim. And it's always going to be the case for all sentences of the form no S are P, that this overlap region between their two circles in their Venn diagram will be always shaded. An E claim is also universal because no is saying none, making a universal claim about the entire class of reptiles and saying that entire class of reptiles, none of them are dogs. So it's a universal claim. But instead of being affirmative like the A claim, it's negative. An E claim is a universal negative. An E claim has the form no S or P. And on a Venn diagram, an E claim shades the middle. So E claims and A claims are our two kinds of universal categorical sentences in standard form. Anytime we're making a universal claim about the connection between two categories, it's either an A claim or an E claim or can be translated into one. This is important. But universal claims aren't the only kinds of things we can do with categorical sentences. We can also make particular claims. So I'll erase this and we'll move to our I claims and our O claims. Let's go back to the example that we had originally, where our blue circle represents the set of brown things, and our green circle represents a set of dogs. Again, something that's brown but not a dog could be soil, and that's both brown and dog, could be Bailey. Something that's a dog but not brown could be Ronnie. Bailey's a chocolate lab, Ronnie's a golden retriever. Okay, so what can I say about the relationship between these two categories? Again, I can't make any universal claims. None of these regions are going to be shaded. Something exists in all four possible regions of this diagram. There's something that's neither dog nor brown. There's something that's not brown but dog. There's something that's both brown and dog, and there's something that's brown but not dog. So I can't make any universal claim. None of these regions are going to get shaded, indicating that they're empty. But I do know that at least one thing exists in a couple of these regions. So I have two different types of ways I can say this. One sentence I can say that's true is I can say that some brown things again, brown things being represented by this blue circle here. I can say that some brown things are dogs. What I'm saying when I say that sentence is that there's at least one entity in this middle region of space, this lens-shaped center region. We represent that on our diagram with an X. That X means, even before I've filled in what Bailey and Ron are, that X means that something exists in the intersection. Here, when it's brown and dogs, we know it's Bailey. But even if we replace brown things and dogs with any two categories, if I say that some S are P, then it always means that there's something in this middle region. Oops. And there's another sentence that I can say about this set of this world as well. I can also say some brown things are not dogs. So as I'm writing this out with a mouse, which is notoriously difficult, should have used a stylus or something. Think about where the X on the diagram will go if I'm representing this lime green sentence. Think about where the X will go if my sentence form is some S are not P. Well, it's going to go in the things that are brown, but not dogs, or S, but not P, which is this region of space. So now we've gone over 4 different types of categorical proposition. We've gone over the universal affirmative, all S or P. We've gone over the universal negative, no S or P. We've also gone over 2 particular claims. The I claim and the O claim. So our I claim is particular and affirmative. So we're not making a universal claim here with our I claim. I claim particular affirmative for our I claim. Our O claim, sure this is clear. Our claim is particular and affirmative. Our O claim is also particular. Yes, it is also particular. But this time it's negative because of this not. Some brown things are not dogs. So if I'm comparing between the set of brown things and the set of dogs, I can use my categorical propositions to tell you that something is in this region of space or this region of space. If you have questions, please let me know. I'd be happy to make any videos getting into more details of any of these ideas. So now we've gone over 4 types of categorical proposition and how they're represented on a Venn diagram. This is important because it can help us to make inferences. If we can really understand how these sentences get represented and why, then when we represent them, we can even represent purely the form of the sentence and be able to tell if an argument is valid or not, even without knowing which entities we're talking about. When a sentence makes a categorical claim about all members of a category, for example, we can diagram out what that sentence means. And if it's logically connected to some other sentences, then we can use a Venn diagram to see if it is valid or not, if the argument being made is valid. So how do we get from here to there? So we've represented 4 types of sentence on a Venn diagram. Now we want to move to thinking about having the representation of 2 sentences on the same Venn diagram, which might involve now having 3 circles. 3 circles is the most we'll do for this particular video in this particular exercise. In theory, there's no reason why you couldn't have 5, 10, a million. A million would probably be pretty hard to draw on a picture, but the same principle would apply. So let's think through what each region of this space now represents. Let's stay with our previous example. I'm going to switch from lime green. I don't like it. I'm going to switch to white. Let's say that this circle represents a set of brown things. This circle represents a set of dogs. And this circle represents the set of, let's think of something that can be, we want something to exist. Okay, I had to think for a second. How about the set of pets here? I just want to choose something where something will exist in all regions of this space. So we have, I'll number the regions. Just so we can see that there are 7 regions, really 8 if we also count outside of them. Region 1 here represents the set of things that are not pets, not dogs, but are brown. So again, my example of soil can work for that one. Soil is brown, but it's not a pet and it's not a dog. Okay. Now, what about region 2? What does region 2 represent? Region 2 represents things that are pets and brown, but not dogs. So any pet that you might be able to think of that's brown, but not a dog. So maybe a brown cat. Hey, oh, I had a cat. A lady that was brown and a cat. Not a dog, but brown and a pet. So that would be in region 2. Region 5 would represent the set of things that are pets, but not brown and not dogs. So Lance, my cat, is white and orange. He's not brown, so he would go in this region of space. Region 3 represents the set of things that belong to all 3 of these categories. Things that are brown and dogs and pets. So Bailey goes here because she's a chocolate lab, she's brown, and she was someone's pet, and she's a dog. Region 4 represents a set of brown things that are dogs, but not pets. So it would have to be like a wild chocolate lab. I don't know one by name because if I knew them by name, they probably wouldn't be wild. But if you could think of a wild chocolate lab that's nobody's pet, but is brown and is a dog, then it would go in region 4. Region 7 contains the dogs that are not pets and not brown. So region 7 would be any wild dog that's not brown. Wild golden retriever. Is there a wild golden? There must be. There must be at least one. A wild golden would go in region 7. Region 6 contains a set of things that are both pets and dogs, but not brown because they're outside of the purple circle. So region 6 contains Ronnie, who's a golden retriever. He's somebody's pet and he's a dog, but he's not brown. So, and again, region 8, my phone. My phone's not brown, my phone's nobody's pet, my phone's not a dog. They're just examples, just one example of things that might exist in each of these regions. Just to show what each region of a 3-circle diagram could represent. And again, no in principle reason we couldn't proliferate this and have 1 million diagrams. But given that our 3-circle diagram has 8 regions, a 4-circle diagram would multiply that even further. Give me a sec. Okay, so yes, with a 4, hypothetically, if you could do a 4-circle, then it would have to have 16 total regions. But it's really hard. It might even be impossible to correctly draw a 4-circle Venn. It's kind of more conceptual. In theory, you could have something that represents that intersection. But it gets more difficult the more and more categories you're drawn to the mix. But that's okay. We only need 3 to be able to make a ton of awesome illustrations of categorical inferences. So this is just to demonstrate what each region of the 3-circle Venn can represent. To make categorical inferences based off them, we need to put together what we learned about how to represent sentences in categorical logic. We need to put that together with our understanding of argument validity. So I'll illustrate with one syllogism. So let me replace my labels with just symbols. So let's say my purple square represents S. My blue square represents P. My green square represents M. Now, different logic textbooks have different standards for which one's supposed to go on the left versus right versus the top. So you, depending on which textbook you're looking at, you may see these organized differently, but the content is the same. You'll still be able, it doesn't matter where you put the terms on your Venn, as long as you represent your sentences correctly. So in order to use a Venn diagram to test for validity, what we do is we observe a categorical syllogism. So here's an example. All SRP, all P, RM. So all SRM. Again, the ordering that I've put the subject and predicate in the middle, this is not the standard ordering, but all I'm doing is illustrating what the process for using the Venn test for validity looks like. Step 1 is to diagram the premises. Here, we only have universal premises, so this is already going to be the case, but just if we had both universal and particular premises, then the universal premises would always need to be diagrammed first. So let's diagram our premises. I'll use light green for premise 1. All SRP. So how do we diagram all SRP now that we're on a 3-circle diagram? I see students getting confused about this all the time, so let's really break it down. We're in a video, so if this is going too slow for you, just skip ahead or don't watch it. It's fine. I'm going to just go super slow to explain why. So again, remember what the set region 1 represents. S, not P or M. That's what region 1 represents. Region 4 represents S and M. Region 7 represents M, but not S or P. Region 6 represents P and M, but not S. Region 5 represents P, but not S or M. Region 2 represents P and S, but not M. Why? This isn't something you would need to memorize. This is just because the green circle represents M, the blue circle represents P, the purple circle represents S. So region 2 represents a set of things outside the green circle, but look, it's inside both the blue and the purple circle. So that means it's something that's P and S, but not M. So in our previous example, it was a pet and it was a dog, but it was not brown, or a pet and it was S was brown before. It was a pet and it was brown, but it was not a dog. So lady was in region 2 there. Okay, and then region 3 represents the set of things that are all 3. Okay, so without knowing anything about S, P, and M, this is all we have, is we have a representation of conceptual space that tells me where any object in the universe would go. Oh, region 8 represents something that's none. Okay. Okay, so going back to diagramming, premise 1 tells me that all S are P. So what does that tell me? It tells me that some regions of this map are going to be empty. Which region specifically? Well, if all S are P, then any region of space here in which something is S but not P, and I'm noticing I forgot to write that here because look, it's outside the P circle. Any region of this diagram that is S but not P becomes shaded because that region must be empty. Remember, shading means it's empty. So which regions get shaded then to represent premise 1? Region 1, because that includes things that are S but not P. And region 4, because that includes things that are S but not P. Now, the thing that students sometimes get confused about is that sometimes students are tempted to just shade this region of space. But notice that region 4 contains things that are S but not P. It doesn't matter that they're also M. Premise 1 tells us that all S are P. It doesn't say anything about M. So just because this is also M doesn't mean that it's being S but not P makes it satisfy premise 1. So again, looking at our previous example, P represented the set of pets, S represented the set of brown things, M represented the set of dogs. So region 4 contains something that was both dog and brown, but not a pet. A wild chocolate lab we put in region 4. Now, if someone came in and told me from on high, hey, all brown things are pets. This is hypothetical, a little tough to imagine, but it would mean that soil doesn't exist or it's not brown. It would also mean there's no brown chocolate lab that's not a pet as well. Region 4 would get shady too. Anytime all SRP. One way to remember this is the shape of the shading for any categorical proposition is always either this crescent shape or a lens shape. We're never shading this like middle type of thing. But now let's shade premise 2. All P are M. So if all P are M, then what gets shaded? Well, the set of things that are P but not M, which regions represent objects which are P but not M. That would be regions 2 and 5 here. Regions 2 and 5 represent things that are P but not M. So we can shade that. Okay, so that's step 1. We've done step 1 of our diagram, our validity test. Check. Step 2 is to see if the conclusion must be true on your diagram. So we don't diagram the conclusion. We just check whether it's already contained in the diagram of our premises. So if it is already contained in the diagram of our premises, then that means our argument is valid. If it's not already contained in the diagram of our premises, then that means our argument is invalid. So in this case, our conclusion says all S are M. So is the conclusion, is it true on this diagram that all S are M? Well, this region of space is empty, nothing can go here. This region of space is empty, nothing can go here. There's only one region of space left for S things to go. If anything is S, it must go in region 3 because all of these regions are empty according to our premises. So if we're living in a world in which we have these 3 categories only, in which sentence 1 and sentence 2 are true about the intersection of those categories, then could we conclude that within the rules of that world, all S are M? Yes, we can, because the only possible way for an S to exist in this world is to exist in region 3. That's the only thing that's not empty in the purple circle is region 3. And check it out, region 3 is also within the blue circle, which is M. So that means that this particular argument is valid. I can make another video running through more examples. I can also answer any questions or go through anything in more detail here that we want to get into. But the whole point of this video was to really break it down in terms of what the Venns represent, to hopefully make it clearer why we use them to demonstrate validity for categorical arguments. So let me know if you have questions, and if you stuck around this long, great job. 2 thumbs up. Have a great day.